In this video, we're going to be learning about the real and complex zeros of polynomials. So to get started, we're first going to talk about complex numbers. Complex numbers are what we call imaginary numbers. So if earlier in videos from past lessons, we have learned how to find the square root of numbers. So the square root of 25 is 5, the square root of 16 is 4. But when you try to find the square root of a negative number on your calculator, you're going to get an error message. So for that reason, we invented what we call imaginary numbers. So every time you have the square root of -1, since it's not a real number, we replace it with an I, representing an imaginary number. Now here I went ahead and put an extra note. We're not going to go into depth in this lesson, but we will be talking about it later. So I just wanted to incorporate it into your notes. If you were to square both sides, you're going to get the fact that I squared is actually -1. But again, we're not going to talk about that one as much today. I just want to focus on this. Every time you want to find the square root of a -1, you could just replace it with an I. Right? So for example, when you have the square root of a negative number, as we have here, this is what you're going to do. You're going to erase the negative. So it's just going to be the square root of n, but the negative that you erased is going to be compensated with an I. Okay? Now, just please make a note of this. When you compensate it with the I does not go inside the square root. Okay? It goes next to it. So for example, if we were given this problem, the square root of -4, again, if you put it in your calculator, you're going to get a message that says non-real solution because it's not possible. It's not a real solution. It's an imaginary solution. So what you're going to do is the square root of -4, again, like we said, we're going to erase the negative. So it's just the square root of 4, but we're going to compensate it with an I, just so the reader knows that there used to be a negative inside. Now from here, super simple. We know that the square root of 4 is 2. So this just becomes 2. Okay, so from now on, again, the square root of 4 we know is 2, and we know that the negative is going to be replaced with an I. Okay, so again, the reason of going over this is because we're going to be seeing that later on in this lesson. Now, this is what we're going to get into doing. So in these types of questions, they're going to give us a polynomial and ask us to find the zeros. The first thing we're going to have to do is find a list of possible zeros, right? So we have a start and we know where to begin. So the rational zeros theorem is going to help us come up with a list of possible answers or possible solutions to a problem. So what we're going to do, it's a 3-step process. Step 1, we're going to find what we call our p-values, and your p-values are going to come from the constant term. So make sure your polynomial is in order. The constant term is the term that doesn't have an x. Now, you're going to list all the factors. Those are going to be your p's. Now, we're also going to find our q's. Q's are going to be the list of all the factors of the leading coefficient. In case you forgot, the leading coefficient is the number in front of the x with the highest exponent. Okay, so that's all we're going to care about. We're going to care about the constant term, the one that doesn't have an x, and we're going to care about the leading coefficient, the one that has the x with the highest exponent. Now, once you have your list of p's and q's, the third, we're going to make all possible combinations of p's over q's. We're going to come up with a bunch of fractions where we divide the p's by the q's. Just make sure we're not going to do it backwards. It's never going to be q's over p's. It's going to be your p's over your q's. All right, if this makes no sense, don't worry. Here comes an example. So here they're asking us to list all the possible rational zeros of the polynomial below. Just like I said on the last slide, we only care about 2 things. We care about the constant term and the leading coefficient. So we're going to go ahead and start by step number 1, finding all the factors of the constant term. Again, constant term means the one that doesn't have an x. So these are going to be your p-values. So what are all the factors of 5? 5 only has 2 factors, 1 and 5. Factors are the numbers that can divide 5. So the only numbers that can go evenly into 5 are 1 and 5. Now that's p's. Now for q's, we're going to look at the one with the highest exponent, which is here. The leading coefficient is -2. We're going to have to find the q values. Okay, what are the factors of 2? Well, just 1 and 2. Those are the only numbers that go into 2. Again, if you're like, why didn't you not include the negative? Don't worry about the negative, and I'll tell you why in a bit. So regardless if the 5 would have been negative or the 2 would have been positive, it doesn't matter. You just list the factors, regardless of sign. Okay, so we have step 1 and step 2 done. Now step 3 says to create all the possible combinations of p's over q's. This is what I mean, okay? So this is what you're going to do. You're going to come over here and you're going to divide all of these numbers by the numbers down here. So let's go ahead and start. 1, let's go and start with the first one. 1 divided by 1 gives me 1. That's how I got this first one. And then we move on to the second one. What is 5 divided by 1? Is 5. That's how I got the second one. Okay, now I'm done with this one. So now I'm going to divide them by 2. So what is 1 divided by 2? It's 1/2, and that's already simplified, so I write it down. And then I move on to the next one. What is 5 divided by 2? 5 over 2, and it's already simplified. And there you go. That's actually all your list of possible rational zeros. That means that if we were to solve this problem, one of these could be the answer. That's what the list is for. That's why it's important, because it gives you a foundation of where to begin checking. Make sure you also make a note of this. Your final answer actually consists of a total of 8 possible rational zeros, because all of these answers could be answers, but there's also their negative versions. So every time you list possible rational zeros, you have to include a plus and minus at the beginning. This means that we could have a 1, but we could also have a negative 1. We could have a 5, but also a negative 5. We could have a 1/2. We can also have a negative 1/2. And lastly, we have a 5 over 2, but it could also be a negative 5 over 2. Okay, so this little plus and minus here saves us the trouble of actually having to write them all down. 1, -1, 5, -5, and so on and so forth. So just make sure you always include that at the very end. So again, that's why we don't care about the signs at the beginning, because at the very end, they could either be positive or negative anyway. All right, let's try another one here that's going to be a little bit longer. Just so you know, I can give you a huge polynomial, but again, the only two things you care about are the constant term and the leading coefficient. So the constant term in this one is the one that doesn't have an x, which is right here. This is where I'm going to get my p-values from. So the p-values are going to be the factors of 64, which are listed right here. So again, you just have to know your times table. So 1 times 64, 2 times 32, 3 doesn't go into 64, so I skipped it. 4 times 16. 5 doesn't go into 64. 6 doesn't go into 64. 7 does not go into 64. And then I find that 8 times 8 goes into 64, or gives me 64. So that's where I stop. So those are all the factors of 64. Now, the q values are going to come from the leading coefficient. So which one's the highest exponent? It's this one. So the 9 is where I'm going to be getting the q values. So what are all the factors of 9? So 1 times 9, and then 3 times 3. That's it. Those are all the factors of 9. And then from here is where it's going to get interesting. Do not freak out, okay? The list of possible rational zeros is going to be all of that crazy stuff, right? So again, how did I get those answers? Don't worry. You come and you divide all of these numbers by 1, which hopefully you should know that it just makes them stay the same, right? So I still get all of those. So I'm done here. Now I come and I divide all of those numbers by 3. So 1 over 3, 2 over 3, 4 over 3, 8 over 3, 16 over 3, 32 over 3, and 64 over 3. So I read those right here. Again, just notice, if any of these fractions could have been simplified, I would have to simplify them first. But in this one, none of them could be simplified. So that's why they stay as is. So for example, if this problem here would have been 9 over 3, that would have simplified to 3. And since you would have them over here on this side, you could put them there. But the order does not matter. But just know, please make a note of that. If the fractions can be simplified, they have to be simplified. Now, if for some reason one of the fractions simplifies to a number you already have on the list, you don't have to write it again. All right, I already divided all of these numbers by 3, so I'm done. And then I still have to come back and divide all of these numbers by 9. So 1 over 9, 2 over 9, 4 over 9, 8 over 9, 16 over 9, 32 over 9, and lastly 64 over 9, which is the ones I got here. Okay, and then again, don't forget your plus and minus at the very front. So all of these are possible rational zeros of the polynomial. Okay, so now we know how to find the list of possible rational zeros. Now we have to actually find the ones that are actual zeros or solutions to the polynomial function. So these are the steps we're going to be doing. When they ask us to actually find the zeros, not the possible zeros, but actually the zeros that solve the function, we are going to follow the following steps. So step number one is we're going to use the graph. If you graph a polynomial, you can actually, if you get lucky, find all the answers to your problem. Sometimes, as you'll see in the problems we're going to be doing in a bit, you can only find certain solutions. But if you get lucky, some of the graphs will give you all of the solutions. So we're going to go ahead and graph to find the first zeros, or maybe all zeros. We'll find out. Step two, welcome back synthetic division. We're going to be doing it again. We're going to use synthetic division with each zero that we find in step one. And if you want to make a note of it, we only need step two if we still have answers missing. Like I said, if the graph gives you all of the answers, then you're done. You don't have to do the rest of the steps. So if the graph only gives us a certain amount of zeros, we're going to have to find the other ones by after using synthetic division. So step two, use synthetic division. Step three, we're going to repeat their synthetic division until the results of the synthetic division can be written as a quadratic equation. Again, if this doesn't make sense, don't worry. We're going to be doing an example in a bit. Step four, once we end up with a quadratic equation, and if you don't remember what a quadratic equation is, it's a polynomial with degree of 2. So you're going to be working on the problem and breaking it down until you can have a polynomial with a degree of 2. Once it's a quadratic equation, we're just going to solve it. Now, please make sure you note this down. The counting multiple roots separately or multiple zeros, the number of zeros is always going to be the same as the degree. This is very important. So if a polynomial has a degree of 7, that means you're going to have a total of 7 answers. So you're not done until you give me 7 answers. If our polynomial only has a degree of 2, that means you're only going to have 2 answers, and that's it. So let's go ahead and put these steps into practice. Here we have a polynomial. The first thing I want you to do, again, I know it says to graph, but before we do that, what is the degree of this problem? Okay, the degree is the highest exponent. So the degree of this problem is 5, meaning that we will have a total of 5 zeros. So we are not done with this problem until we have a total of 5 answers. So step number 1 is graph this. So you could use your graphing calculator. If you don't have a graphing calculator, you could use a website called desmos.com. Let me go ahead and write it down here. It's a graphing calculator online, and you're more than welcome to use this one. So we're going to, and I'm so sorry about my handwriting, but you could use Desmos. So it's desmos.com. It's a graphing calculator where you have to put y equals and then put this whole thing down. Okay, now you're going to get something like what I have here. Again, if you're using a graphing calculator, you go to y equals, you write all of this down, and then you just graph it. And then look at this. We're supposed to have a total of 5 answers. Let's see if the graph gives us 5. So what you're going to do is that you're going to look for x-intercepts. Remember, zeros is the same thing as x-intercepts or roots or solutions. They all mean the same thing. So let's come over here. Let's see how many answers the graph gives us. There's an x-intercept right here. There's an x-intercept right there. So that's a total of 2. There's another x-intercept here. So that's a total of 3. And then there's another x-intercept here, which is a total of 4. But remember, we're supposed to have a total of 5 answers. So I know it looks like we're missing 1, but you should remember this from a previous section. When a graph touches and turns, you should remember that that means it has an even multiplicity. So actually, this number counts as 2 solutions. Okay, hopefully you were able to catch that. When the graph touches and turns, because remember here the graph crosses, here the graph crosses, here the graph crosses. So those all count as just one solution. But hopefully you remember that when a graph touches and turns back, that solution or that x-intercept counts as 2 because it has an even multiplicity. So technically, look at that, you guys. We got lucky with this one. We don't have to do any synthetic division. The solutions are right here. So my zeros are going to be the one right here, which is -2, the one right here, which is -1, this little number right here, which is 2, and then this one, which is 3, counts, like I said, counts as 2 zeros. So that's why I listed it twice. And then look at that, 1, 2, 3, 4, 5. I have a total of 5 answers. So that was pretty fun, right? We just graphed it and voila, we found our answers. Okay, let's try another one here. Find the zeros of the polynomial. Again, the first thing we do, the degree is 4. So that means I have to have a total of 4 answers. So let's graph this and see if we get lucky just like with the last one. So if I graph this, I find 1, 2, 3, 4. Look at that. The graph gave us all of our 4 answers once again. But the reason I want you to see this problem is because this right here is a decimal. You're not allowed to give me decimals as answers. They have to be exact form, meaning there has to be a fraction. So if you don't know what this number is as a fraction, you are going to have to figure it out. But this is where the rational zeros come into play. So here is a list of rational zeros, and you're like, oh my goodness, where did she get that from? I got it from the previous problem we did a couple of slides back. Remember how I found the whole list of rational zeros? Now, all you have to do is just try all of these fractions until you find the one that gives you negative 1.33. Because remember, these were possible zeros. So actually, one of these is this right here. So if you keep on trying them, right, divide all of these numbers by 3, so to see which one it is, you'll find that it's actually 4/3. So this one is a decimal, but we found it to be negative 4/3. And if you have no idea how I did that, just grab your calculator, divide negative 4 by 3, and you get negative 1.3333, right? So that means that's the first zero. This one right here ended up being, actually this one belongs to this one, sorry. This one is negative 4. This one belongs to this one, which we already found was negative 4/3. This one is at 1. So that's our third zero. And in this one, again, it's a decimal, but it's actually 4/3. And again, you don't have to double check, right? The negative 4/3 gives us the negative version, so the 4/3 gives us the positive version. So there you go. We have our 4 answers. And again, no synthetic division needed because the graph actually gave us the 4 answers. But we did have to kind of go through the struggle of finding which fraction was the one that was denoted on the graph, just because it was a decimal. So obviously, if this would have been a 0.5, hopefully you guys can agree it would have been the 1/2, but it was 1.333. So we found it to be 4/3. Okay, so look at that. Those would be your 4 answers to this problem. All right, we still have a couple more examples. Let's go ahead and try one more. Find the zeros of the polynomial. We have a polynomial there. The degree of this polynomial is 3. Again, that's the highest exponent. So that means I'm not going to be done until I have a total of 3 answers. So I go ahead and graph this. Again, you could do it through decimals or you could do it through a graphing calculator. And I found this right here. Now, I have 3 solutions. I notice one of them is pretty because it's a whole number, but I have 2 decimals. So let's see if it's one of the fractions. So I come up with a list of possible rational zeros. But here's the issue. If I list all the possible rational zeros of this problem, and if you don't remember how we did that, remember it's p's over q's. So it's the factors of 2, which is 1 and 2, over the factors of 1. The factors of 1 are just 1. So 1/1 gives me 1, and then 2/1 gives me 2. So those are all the possible rational zeros. There's no fractions in here. So this number cannot be represented as a fraction, and this number cannot be represented as a fraction. So we're going to have to find those answers on our own. All right, so I know that's the answer, and I have it, but it's a decimal. And remember, our answers have to be in exact form. So this is what we're going to do, and this is where we're actually going to be using the steps we learned earlier. So step number 1 was to graph it. We graphed it. And we found 3 zeros, but unfortunately, 2 of those are not in exact form. So I'm going to have to be forced to use this one, which is actually a pretty whole number. Or not a whole number, but an integer. So I'm going to go ahead and use that number. And according to the steps, we're going to have to do synthetic division. So hopefully you remember what synthetic division is about. In here, you're going to use the 0 that you found in the graph, which we found -1. These numbers, hopefully you remember, are our coefficients of our problem. So here is the 1. Here is the 3. The 0 represents the x value. There's no number here with an x, so that's the 0. And then the -2 is a number that doesn't have an x. Okay, and then synthetic division, in case you forgot, we bring this one down. and then we multiply. Negative 1 times 1 gives me negative 1, and then I add. 3 minus 1 gives me 2. Negative 1 times 2 is negative 2. I add, I get negative 2. Negative 1 times negative 2 is 2, and then I add and I get 0. You have to get a 0 here. Okay, if you don't, then we did a problem wrong. Because according to the graph, negative 1 is supposed to give me 0. So that turned out nice. Now, the whole point of doing that is because now this problem, and again, you should know this from a previous video, can now be converted into this polynomial. Okay, so look at that. The degree was 3. So after the synthetic division, now the highest exponent is going to be, instead of a 3, a 2. And then you just go in descending order. X to the second power, and then x to the first power, and then the number that doesn't have an x. I translate that into a polynomial, and I have 1x squared right here, 2x right there, and then the minus 2 right there. Okay, so we did synthetic division, and go back to the steps. We do synthetic division until the result can be written as a quadratic equation. And this right here is already a quadratic equation because the exponent is 2. So now what we're going to do is we're going to have to solve this problem. And when we solve this problem, we're going to find the last 2 solutions. And we're going to learn how to write them properly. All right. So now we are stuck with this problem and we're going to have to solve it. Again, you guys know how to solve quadratic equations already, right? There's different ways. We could try factoring, but I'm going to let you know that this one's not factorable. So we're going to have to go straight to, don't forget, the quadratic formula. Remember, the quadratic formula is always here to save the day. So what we're going to do is we're going to find our A, B, and C. So A is going to be the number in the front. So that's A. B is the 2, and C is going to be the negative 2. So in case you forgot the quadratic formula, it's negative B plus or minus the square root of B squared minus 4AC all over 2A. And then I just replace the values. So negative B, which is 2, plus or minus the square root of B squared, which is 2 squared, minus 4 times AC, which is 1 and negative 2, all over 2A, so 2 times 1. All right, from here, I'm just going to go ahead and jump through the steps real quick. I multiplied all of this, which gave me positive 8. I did the 2 squared, which gave me the 4, and then I did the 2 times 1, which was 2. I proceeded to add the 4 and the 8, which gives me 12. And then remember, when you have a square root, you have to simplify the radical. So I found out that 12 is actually 4 times 3. And you could have also done 2 times 6, but neither 2 nor the 6 are perfect squares. So that's why I went with 4 and 3, because the square root of 4 is 2. So I took out the 2, and the 3 just stayed inside. Okay, so hopefully you're okay up to there. Now, after this, remember, we simplify all of these numbers. And all of those numbers can be divided by 2. So the negative 2 becomes negative 1. 2 divided by 2 becomes a 1, which I didn't write down, but it's an invisible 1 right here. And then 2 divided by 2 gives me 1, which is an invisible 1 down here that I didn't have to write down. And then look at that. Those are my 2 final answers. So I have the negative 1 that I got from the graph. And then I have the negative 1 plus the square root of 3, which comes from here. And then I have the negative 1 minus the square root of 3, which also comes from here. Okay, and then here's the fun part. If you put this in your calculator, negative 1 plus the square root of 3, you're going to get this answer right here. And then if you do negative 1 minus the square root of 3, you're going to get this answer right there. So again, I know the graph gives you all of the answers, but you do have to write these in exact form, meaning it has to be in fraction form, which this was not the case, but it was in square root form, which we had to find by using the quadratic formula. And there are our 3 answers. All right, let's go ahead and wrap this up with one last problem. Find the zeros of the polynomial. We have, again, a polynomial of degree 3. So since it's a degree 3, it means I'm going to have a total of 3 zeros. Okay, so again, let's go ahead and start graphing. Cross our fingers that hopefully we get 3 answers, but unfortunately, we only get 1 answer. So we have a total of 3 answers in total, but the graph only gave us 1 of them. And the bad thing is that it didn't even give us a pretty one. It gave us one that was in fraction form. but no problem. Let's go ahead and see. Negative 3.333 is actually negative 10 over 3. Okay, and again, if you're not sure how I got that, you would have to list all the possible rational zeros, but I'm going to leave that up to you. And then you could try every single one of them until you see which one gives you negative 3.3333. All right, we found that to be negative 10 over 3. Now, like I said, we're supposed to have a total of 3 answers, and I only have 1. So that means we are going to have to do synthetic division. And yes, with a fraction. So here's our synthetic division. That number obviously goes right here, the one that we found on the graph. And then here we have all the numbers, the coefficients from our problem. So we have the 3. What comes after x to the 3? X to the 2. So that's the second number. What comes after x to the 2? Just the x. So that's the third number. And then after x comes a number with no x, which is the 90. So in this problem, we didn't have to put a 0 as a placeholder like we did on the last problem. Okay, now from here, we drop this down. In your calculator, you could do negative 10 over 3 times 3, which gives you negative 10. We add, that gives a 0. Negative 10 over 3 times 0 gives a 0. And then we add, that gives me 27. And then negative 10 over 3 times 27 gives you negative 90. You add, and that gives you 0. Again, this was supposed to be 0. Okay, now like we did on the last problem, we're going to convert this into a polynomial, which is, oh my goodness, right there. So again, the degree was 3, meaning that our new answer is now going to have a degree of 2. So this is going to be x squared. Now what comes after the x squared? Just the x. And after the x comes the one that's just the number. So this is what it translates to. 3x squared plus 0x plus 27. Hopefully you agree with me, when you have a 0x, you don't have to write it down, so it just converts into 3x squared plus 27. Now, the whole point of doing that is now that I'm just going to focus on that smaller problem. And if I can solve that problem, I'm going to find the 2 missing answers that I have missing, right? So we're just going to focus on that now because we already have 1 answer. I have to find the other 2 from here. Just like we did on the other one, if you love the quadratic formula, then just use the quadratic formula. The quadratic formula is going to give you your 2 answers. So your A value is going to be 3. Your B value is going to be 0. Let me just go back, right? Because of this right here, this is your B, which I didn't write down, right? But that's going to be your B. And then the 27 is going to be your C. So again, if you want to use a quadratic formula, use the quadratic formula. Now, I'm just going to show you something real quick. When you have 2 variables like this or 2 terms, you could go away without using the quadratic formula. So I'm going to show you, since we already used the quadratic formula on the last one, I'm going to show you how to do it when you don't have to use the quadratic formula. So if I want to solve this, I just grab it and I set it equal to 0. And then I could simply just solve this by moving the 27 over. So if I move the 27 over to the other side, I'm going to have 3x squared equals negative 27. Now to solve for x, I'm going to divide both sides by 3, which gives me x squared. And then if I divide both sides by 3, 27 divided by 3 is going to give me 9. And negative divided by positive gives me negative 9. Now in order to get rid of the square, I'm going to square root the left side and I'm going to square root the right side. These 2 cancel out, leaving me with just x. And then on this side, I'm going to have the square root of negative 9. Now again, this goes back to the beginning of the video. If you want to find the square root of a negative number, remember you can't. Try it on your calculator. It's not going to let you, but we already learned how to do this. We know that the square root of 9 is 3. And then remember the negative, you compensate it with an I. Okay? Now, one little thing that we have missing here, remember when you square root both sides, you always have to add a plus and a minus. So this was supposed to be plus and minus, plus and minus. That means my final answer is technically 2 answers. I have a positive 3i and a negative 3i, which is just what we needed. Because remember, we were supposed to have a total of 3 answers. We have 1 from the graph, and now we have the other 2 missing right here. So our final answer is going to be negative 10 over 3, which again comes from the graph, and then the 3i and the negative 3i that we got from the problem. Again, If you love the quadratic formula and you just can't live without it, then go for it. Use the quadratic formula, you're going to get the same two answers. But just please note, when you have two terms like this, you can go about without using the quadratic formula. But if you want to use it, go for it. So there you go. Those were our three final answers for this problem.